Hello guys, this is Anno from the Xzistor lab, and in this video we'll take a look at how the Xzistor concept brain model can affect motion in a little robot like Troopy, our little Lego robot. And here we have Troopy propped up on a plastic box, so we can take a good look at his motors today, and get some idea of how the model achieves all the motions required for the robot to move around autonomously, and also for the operator or the tutor to drive the robot around its confine. So one of the reasons why we use the EV3 Lego brick for this robot was actually the fact that the motors are fully integrated with the system. So no integration is needed, no soldering or calibration is needed. That, along with the fact that the EV3 brick has also got all the sensors integrated already onto the little computer. So that makes it very easy to work with these motors. And I'll just zoom in a little bit so we can see what they call the large Lego EV3 motor. We'll talk a little bit more about that. I'll just put up the spec for this motor after this, but I just want to show also the motor above here, slightly hidden, but that's the medium sized Lego motor. So in this robot we use two of these large Lego motors to achieve the differential drive for the robot. Basically we drive the robot like a battle tank, and it drives itself like a battle tank. And then we have this medium-sized motor here which drives the arm and allows the right arm of the robot to move up and down and point at buttons and point his laser gun and maybe push some buttons on his mobile phone.
Let's look in more detail at the EV3 large regulated motor. This is exactly the motor that we're using on Troopy. And if we look at the specification, we see we have tacho feedback to 1 degree, which allows us to control the speed of the motor quite accurately. This is quite important for the Xzistor concept brain model, especially if we want the robot to learn to repeat certain motions. 160 to 170 RPM. We have a running torque of 20 Newton centimeters, a stall torque of 40 Newton centimeters. This becomes important when we want to model fatigue in the brain, and we will talk more about that in the fatigue demo video. The motor's got an auto ID, which is helpful because the EV3 brick will immediately recognize the motor once connected, and that makes it just so much easier to integrate the system. When we look at the EV3 medium regulated motor, this is the one we use to lift Troopy's right arm up and down. If we look at the specification here, again we see we've got tacho feedback to 1 degree, which allows us to regulate the motor quite accurately, the speed. In this case 240 to 250 RPM, slightly higher, but then the running torque is lower at 8 Newton centimeters. Stall torque at 12 Newton centimeters, and again the auto ID to identify the motor by the EV3 brick is a very handy feature.
So on the laptop we have implemented the motion buttons to enable us to drive the robot. We use what we call a key listener class, run it in a separate thread from the rest of the robot program, and then just if I use these K and the M keys, K key would make the right wheel go forward, and I'll just push it. So we'll see it starts to move forward. If I keep on pushing the K key, it will speed up. You can hear the moving at quite a high speed now. and then if I push the M key, it slows down again, and with a bit of practice one can actually quite easily drive the robot around the confine. So we use the A and the Z keys on the left hand side for the left wheel, and the M and the K keys on the right hand side, and we will also do the same for the medium motor. So for the medium motor we will want to lift the arm. I'll use the F and the G keys. So let's see what happens if I push the G key. You can see the right arm going up, moving upwards, and that's adequate for us to prove our point. Remember, this is a concept demonstrator. We're not trying to make it too complex, we're just trying to show the principles. So we can see how their right arm is moving up and down by the little medium motor over there. I just want to show, I've actually got the medium motor cover there with a little cover I made from a shampoo bottle, and that's just to hide the worm gear assembly there. I just want to show a simple little worm gear that actually drives the arm up and down, and this is just to make it look a little bit neater. There we go. So that's then the what we call the key listener class that we use in Java, and we run it in a separate thread from the rest of the program, and thereby we can use keys to drive the motors over Wi-Fi. So with the medium motor driving the right arm up and down, we can make Troopy push buttons on his head-up display panel. So for instance, we can teach him to push button number 1 to open his food source. That'll take a few iterations, but eventually he will learn to do that by himself. And we can do some other interesting tests to see his intelligence and his thinking by using this head-up display panel with the buttons on. We can also make him push buttons on his mobile phone using this medium motor. So it's quite an important effector in this model. So when we affect motion in an Xzistor concept brain model robot, we don't just use motors. There are many different effectors we can use. We can use pneumatics, hydraulics, we can use linear actuators, and also on this little Lego robot, on the EV3 brick down here, you'll see we have a little speaker there, which we can also use for sounds, to output some sounds, and we also use the laptop the speakers of the laptop to output some sounds. And also, if you see the facial expression on there, it shows a pretty high level of distress, and that's also effectively a motion output from the brain model. So what's happening on the face, and although we don't have all the muscles pulling the facial expression, we effectively manage it in exactly the same vein. The reason for the distress, of course, is with Troopy being propped up like that, both the color sensors in the front and the back are off the deck, and they are therefore reading black, which effectively tells Troopy that he's just rammed into a solid wall and experiencing extreme pain. So maybe best we get Troopy off his pedestal and return him to terra firma. Now, after that impressive display of Troopy's mobility and agility, let's take a look at some conclusions and thoughts on robot motion. I think the main thing here is that the Xzistor concept brain model allows us to design robots with cognitive architectures allowing for motion, and these motions result from the subjective states that the brain model generates, like reflexes, learning, instinctive fears, urgent needs, past experience, pain, fear, anxiety, pleasure seeking, aggression, joy, fatigue, sleepiness, boredom, curiosity, addiction, intuition. All these states the brain model can generate. We will simply define the devices that actually performs the motions as effectors, and we'll talk about the different types of effectors a little bit more later. The model adjudicates between the competing states, the subjective states in the mind, to conclude the final set of actions, leading to effector external impacts, and that is when the actual action has some impact on the environment, as opposed to an effector internal impact, which happens inside the body of the robot. And we talk about gland excretions here, for instance, and we'll explain exactly what we mean by that a little bit later. If we look at how the motion algorithm is synthesized within the brain model, we see that it's fully integrated with the other brain algorithms and transact with these via strict protocols. The synthesis of the motion algorithm with the rest of the brain is based on a very simple logic cycle, and we see it depicted down here, starting with a checking function. This is actually essentially where the robot assesses the environment using its sensors. This information is passed on to the planning function, where the information is processed and the robot decides what would be the appropriate actions to take, turning these into action commands, and the action commands are passed on to the do function, which is actually our motion algorithm. And because this could lead to the robot having changed something in the environment or having moved in the environment due to wheel motion, it's important to quickly come back to the checking function and reassess what the new status is of the robot. So again, the sensor functions will be passed on to the planning function. The robot will now see what has changed, base new decisions on that, come up with new action commands, and these will be passed then down to the do function again, our motion algorithm. Very simple loop followed, makes it possible for us to design very simple robots, and based on the serialization of the essentially parallel brain. So simple enough. Where it does get tricky is where we have to start decomposing the full complexity of the brain into its constituent parts, and what we will find is that some of the subroutines within the algorithms actually depend on outputs from other subroutines in other algorithms, and this makes it quite tricky to get the sequence right. And it actually it took me a couple of years to get the Xzistor concept brain model sort of sequenced in the right way. So here we see some of the effectors we can use on a robot. We don't need to think that the muscles of a human being should be replaced by electrical motors or actuators. There are many different actuators and effectors we can use, and we see some gauges and meters, lasers, emitters, solenoids, servos, speakers, many different effectors that can be used when we build robots. And there's some more listed there. So electric valves, we've got relays, ailerons, propellers, fans, quite a lot. And I think the four key things we must look at when we define the effectors of a robot is normally they do one or more of the following. They would change the environment, so you can have something like a gripper that moves things in the environment. It can reorientate or change the status of the robot in the environment. So basically, just through wheel motion, place the robot in a new position. It can communicate with others in the environment, send messages, for instance, through LED screen, or it can affect emotion inside the body of the robot, and we'll talk more about that later. Of course, more complex systems is possible with using exactly the same motion algorithm. We can combine motors and actuators into more complex systems, and it's easily handled by exactly the same motion algorithm. And here we see some more complex systems. All of these we can implement quite easily by using the Xzistor concept motion algorithm. And this is typically some of the actuators we will see once we start building more sort of enhanced versions of Troopy and other Xzistor robots. When we have these more complex combinations of effectors, we will see that the motion becomes more coordinated with time, and the robot does that by minimizing effort and avoiding fatigue. And it's interesting to see Troopy when we teach him to walk to his, or to find his food source, how gradually over time his motions become more smooth and more immediate, and how he sort of learns to turn around and walk straight to the food source, whilst when he starts off it's quite shaky and he's quite uncertain, and sometimes he doesn't take the shortest route to the food source. So I think what we're saying is the motion algorithm of this model can handle highly complex systems. No changes needed. It's scalable to up to very, very complex robotic systems. And this is where we see probably the ultimate in complex effector combinations. If you look carefully at the, President Lincoln's face there, so it almost looks like a real person, but this is in fact a robotic sort of an animatronic character that was built by the Garner Holt production studio. Excellent robot, and I just think if I think of the facial expressions generated by the Xzistor concept brain model, how interesting it would be to actually combine that brain model with this system. And I think the time is upon us where some of these robots will become more and more lifelike and start to, it'll be more and more difficult to discern between humans and robots. When we look at speech, people sometimes think speech is a very complex and enigmatic phenomenon, but in the Xzistor concept brain model, it simply is nothing other than a coordinated movement of muscles based on learned behaviors. So once again, it becomes coordinated through practice, and all of this complex motion, the motion algorithm can handle, and it makes it much easier if we use just a speaker instead of all those complex muscle sets that we can see working over there. There's an interesting one, sleeping. So what happens to motion when the robot goes to sleep? So first of all, Xzistor robots can be made to sleep. Troopy does go to sleep when I pushes the right button. So during sleep, robot motions are disabled by modeling the effects of two what they call paralyzing neurotransmitters. The one is the gamma aminobutyric acid, or GABA, and the other one is glycine, just like in the human brain. So we basically drug the brain or switch it off to go to sleep, and that will inhibit certain motions. And the only motion that we retain when we put Troopy to sleep, which is effectively a REM sleep, a rapid eye movement sleep, we just make Troopy sort of move a little bit to the left and to the right, almost like a semi-rotation, just to tell the tutor or the operator that the robot is at sleep, and we don't really want to wake the robot up. Important to note that the Xzistor concept brain model does not model the metabolic processes in the body. So we're not interested in the part of the brain that keeps the human body alive. We are just interested in the cognition and the emotion part of it. So to develop a model like this, it's important to have a basic understanding of the central nervous system, internal organs, metabolism, homeostatic regulation, and so on, and specifically the endocrine system. So what is the endocrine system? Basically a set of glands that can excrete hormones, and we see there in the picture the male and the female endocrine systems. And when these hormones are secreted, it could influence cognition and emotion. If we think about adrenaline, the key role it plays in the fight or flight reflex, and the stress and anxiety that causes very much linked to our emotional state. So the motion algorithm integrates all of these along with all the other effector motions. So when we look at human scalability, we have, by now I think we've made the point that the motion algorithm can drive highly complex systems. It's a more of the same concept, in the sense that it doesn't get more complicated to build more complicated machines. It's just more of the same. We just drop in more and more effectors into the algorithm, and everything else will happen naturally. In fact, we can develop a wizard program, and I've done some work on a wizard program, which actually automatically builds an Xzistor brain. So it will ask you a set of questions about your effectors, what the mission of the robot is, how you want to control the effectors, certain critical ranges that you want to operate the effectors to. And then the code will automatically generate a Xzistor concept brain, an instantiation that you can use and run your robot with. That still needs a bit of work, but it doesn't look like it's going to be very difficult to achieve. Yeah, we can build instinctive animal brains using the Xzistor concept brain model, or we can build human type brains. And interestingly, we can build anything in between. So one of the very exciting sort of revelations of the Xzistor concept brain model was the fact that it so clearly explained what the difference is between an animal brain and a human brain. So we say it can be scaled far beyond the human capability. There's so many examples where we can just expand a robot to, for instance, just have a direct connection to the internet. It could be reading map data real time from the internet, weather data, and adapting its sort of effector motions to depending on what it sort of downloads from the internet. So many functions can be added to a robot. Night vision, certain, for instance, radiation sensing, things we can't see or hear. We can really expand the robot quickly far beyond the human range, and also expand the brain to be much more competent and much more capable than the human brain. The robots that we are going to build based on the Xzistor concept will always have an instinctive sort of reflex to obey a verbal command to stop or reverse motions. So we literally design the robot to listen to certain commands, and if the robot, for instance, the one that we're experimenting with at the moment, where we will just tell robot IQ stop, and no matter what the robot is busy with in his mission, he will stop. Or we can say something like robot IQ 3, which means the robot will reverse 3 seconds of motion, the last 3 seconds of his motion. And this is just in case of an emergency where a robot is trying to help a human being, but maybe inadvertently places the human in a difficult situation. We can make the robot reverse immediately. The Xzistor robots will also have an external motion override button, which will be prominently placed on the robot. So at any given time, a person can hit the button on the back of the robot, and it will do the same thing. It will stop its motion and reverse its motion.
For those of you who want to design your own brain model and maybe test it on an AI platform, the motion algorithm is a very good place to start. And I guess the first thing you'll need is an EV3 Lego kit, so you can buy that either directly or look for some second-hand ones online, and then just build a very simple little robot like this, of which there are many plans and blueprints on the internet, and you can immediately go then and use the Lego programming language to start programming your robot. Alternatively, and that's what we've done with Troopy, is to go for the Legos replacement firmware. So the guys have done a sterling job of developing this Legos alternative, and it even includes a Java virtual machine, which allows us to directly make contact with the sensors and the motors via Wi-Fi. And then I guess just use our simple logic cycle, which we've discussed already, and use that to base your logic on to start off with. And just to give a simple example, let's say you design your little robot to be a line following robot. So it's following a black line, and it's got maybe 2 color sensors on the front. And it'll be as simple as the checking function will then be the one where we say, okay, well, what are those color sensors reading? And let's say the left one is starting to read black suddenly. That's passed on to the planning section. The planning section will say as simple as, if the left color sensor starts to read black, you got to turn left. If the right color sensor is starting to read black, you got to turn right. And in that way, the line following robot will follow the line. And of course, this section will then pass on motion commands to the wheels to either turn left or right. That'll change the position of the robot, and again we will reassess whether that is rectified the situation. Strictly speaking, the little line following robot will then strictly follow the line. And then one can start to add some more intelligence, some more features, even have a go at trying adding some emotion, and try and outsmart Troopy or outcute Troopy. And the main thing is to have fun and enjoy doing this a little project. A good place to start. And I think with that, that's concluding from my side on motion and the motion algorithm of the Xzistor concept brain model. Thank you for watching.